Welcome to the lecture on controllability of time varying linear systems. So, this is the continuation of the last lecture. In the previous lecture we have seen some results on the controllability of time invariant system, that is autonomous system. If you recall some results of the previous lecture, so we considered the system x dot equal to Ax plus Bu, where x of t belongs to Rn and u of t belongs to Rm. So, which is called the state space and the control space. So, x of t belongs to Rn for each t as a constant vector. So, where A is n cross n constant matrix, and B is n cross m constant matrix. So, for this system we have defined the controllability. Roughly means that given any vector x0 and x1, x0, x1 belongs to Rn, arbitrary vectors, it is given, and a constant time t and a real number t, which is the final time of the system. Then the system is said to be controllable if you call this system 1. If there exists a control u of t such that the solution x of t of 1 satisfies x of t0 equal to x0 and x of t equal to x1. So, here given real numbers t0 and t1, some initial time and final time is given and two arbitrary vectors are given x0, x1. If you are able to find a control u of t so that the solution has x0 as the initial condition and x1 as the final condition. So, if it happens, then we say that the system is controllable. So, we have proved that the system is controllable if and only if the rank of the matrix B, AB, A square B, etc., A power n minus 1 B, if it is equal to n. The size of the matrix is n cross m into n. This is for the constant matrices or the autonomous system. Now, if the matrices are time varying, then this rank condition may not work. Even if the rank of let us say A and B are function of t, then if you replace it with B of t, A t into B t, etc., if the rank is equal to n for each value of t, then also the system may not be controllable. So, that we will see that we need a different condition for the controllability of the autonomous system, controllability of the time varying system or the non-autonomous system. So, consider the linear system dx by dt equal to at xt plus bt ut in the time interval t0 to t. Then it is well known that the solution of the system can be written in the form x of t equal to phi of t t0 into x0 plus integral t0 to t phi ts bs us ds. So, this is a non-homogeneous system of differential equations. So, the solution is written in this particular form where phi of t t0 is the state transition matrix for the time varying matrix A of t. So, if you recall the state transition matrix phi t t0, it is e to the power a t minus t0 if A is a constant matrix. So, this is known, and in case it is time varying, if A is a function of t, then the state transition matrix phi t t0 is written as t0 to t as ds plus t0 to t and t0 to s as a s1 ds1 ds plus etc. So, it is a infinite series we will have. So, we will have the infinite series t0 to t, t0 to s etc. t0 to s n minus 1 as plus etc. So, this infinite series represent the state transition matrix, which is called the Peano-Becker series. Now, we can easily see that if A is a constant, then it reduces to the value e to the power a t minus t0. So, using this state transition matrix, we will be able to write the solution of the first equation in the form of the second equation. Now, we know certain properties of the state transition matrix. So, if we again recall the properties of the phi matrix. So, if you take the same variable phi of t comma t is the identity matrix phi of t s and phi of s s1. If we take variables like this, then we get phi of t s1 and phi of t s is phi of s t inverse and d by dt of phi of t s, that is equal to a of t into phi of t s. So, these are the four properties of the state transition matrix. So, it is clear that the state transition matrix is always invertible matrix. So, using the property, we can write the equation 2 in the form of equation 3. Phi of t t0 can be taken out and then we can write it as x naught into, because phi t t0 into phi t0 s will be phi t s. So, we can write it in this particular expression. So, now we will come to the result, that is when the autonomous system, non-autonomous system 1 is controllable. So, first we define the controllability Gramian matrix, which is defined as for the given values T0, T and these two matrices, we can write the expression W T capital T equal to integral T0 to T phi of T0 S B S B transpose S phi transpose T0 S ds. So, this is a n cross n matrix, because phi is a n cross n matrix, B is n cross m, and all this product will give a n cross n matrix, and after integrating each element of the n cross n matrix and putting the limits, we will get a constant matrix W T0 capital T, that is called the controllability Gramian matrix. So, we will show that the system 1 is controllable if and only if the controllability Gramian matrix is non-singular. We can also note that it is a symmetric matrix, because phi into B and phi B transpose, these are multiplied, therefore, it is a symmetric matrix, and if it is non-singular, then the system is controllable. The proof is like this: the initial condition is x t naught equal to x naught, and the solution is written in the form x. Earlier slide we have written the solution in the form of 3. Now, if you substitute t equal to capital T, we will get the final position of the system. So, x of capital T is written in the form given here. Now, if you apply the condition, the property of phi, because phi is invertible, this can be taken to the other side, we get phi t naught t into x of capital T, and take this x naught to the left hand side, we will get the equation 5. Now, by observing this term phi t naught s b s u s d s, if you substitute a suitable function u of s, vector function, and if it is satisfying the left hand side and right hand side suitably, then we can say that this control will steer the system from x naught to x1. So, what we will do is we will just by guesswork, maybe we can say that, or by observation, we can substitute this particular expression, because we have this Gramian matrix phi B B transpose phi transpose. So, we will bring that particular form here. So, u of x can be substituted as B transpose S phi transpose S. If you put that, will, after doing the integration, it will become W. Then we can cancel the W by multiplying with a W inverse. So, after multiplying here, we will balance it with this vector phi of T0 capital T into x1 minus x naught, if you write it. So, if you substitute this u of s in this place, what we will obtain is finally phi of t naught capital T into x1 minus x naught. So, we will get phi of t naught t into x of capital T minus x naught. So, if we substitute this control B dash B transpose phi transpose into this expression, so what we will obtain is, so we will get the value phi t naught t into x1 minus x naught. So, this automatically will imply that x of capital T equal to x1. So, which is the required one. So, we can conclude that this control given in equation 6 will take the system from the initial condition x0 to the final condition x1. So, the system is controllable. So, we can see that this is not the only possible control which will do this work. There may be several other controls available, and so what we require is at least showing one control for the controllability of the system. So, that is the sufficient condition. If the W is invertible, we are able to write like this. So, we have shown that if W is invertible, the system is controllable. Now, we will show that if the system is controllable, then the W is non-singular, or the invertible matrix. So, let the system 1 be controllable, but the matrix W is singular. That is, if you assume that it is singular, then we will arrive at a contradiction. So, if a square matrix is singular, then we will obtain a non-zero vector alpha, so that W alpha equal to 0, where alpha is in the state space Rn. Now, if you multiply both sides with alpha transpose, we get alpha transpose W alpha equal to 0. Now, substituting the expression for W, we will get integral T naught to T alpha dashed. The remaining is the definition of W, phi T naught S B S B transpose S phi dashed T comma S, and then again alpha into ds. So, this first 3 products and the second 3 the next 3 products, that they can be written as the transpose of each other. So, ultimately we will get the value is nothing but B transpose phi transpose T 0 S into this expression. So, it is nothing but integral T 0 to T, we have this expression as alpha transpose phi T 0 S B S and then B transpose S phi transpose T 0 S into alpha ds. So, this expression can be written as this multiplied by this one, they are transpose of each other. So, we can write it as norm of B transpose S phi transpose T 0 S into alpha square ds. So, if this is equal to 0, that is what we have obtained. So, if the positive value, positive function, and if the integral of the positive function is 0 for during in this interval t 0 to t, this implies that the positive function which is available inside is itself 0. Or its transpose is also equal to 0. So, what we will get is alpha transpose phi T 0 S B S equal to 0 for all S value. So, that is what we have. So, this expression is 0. So, from here we can show that the system is not controllable in this case. See, first we have assumed that the system is controllable and W is singular, and we arrive at this expression. Now, we will show that it will give a contradiction to the controllability of the system. So, now we assume that the initial condition is x t naught equal to 0 and the final condition is x of capital T is phi of capital T T naught. Here there is a error. We assume that this x of capital T equal to phi of T T naught into alpha and x naught equal to 0. For this initial condition or for this final condition, there will be a control available because the system is controllable by assumption. So, if we substitute this x naught equal to 0 and x of capital T equal to phi of capital T T naught into alpha, we will get in the left hand side only alpha value and in the right hand side we will get this expression. So, ultimately we will get this as the equation alpha equal to integral T 0 to T etc. Now, multiplying both sides with alpha dashed, we will get alpha dashed into alpha equal to 0 because of this equation 7 here, and hence we will get alpha equal to 0, which is a contradiction to the fact that this W is singular. Okay. Therefore, W should be non-singular for the controllability of the system. So, this result is very useful in computation. Actually, we can make use of this result, that is equation 6 for actual computation of a control which will take the system from the initial condition x naught to the final condition x 1. So, for example, if you take the matrix A to be 0 1 minus 1 0 and B to be 0 1, it is a constant matrix. So, this result we note that it is suitable for both time varying as well as time invariant system. So, for the purpose of simplicity of calculation, we take the constant matrices. So, A is given like this, we can easily calculate e to the power a t in this way, which is equal to the phi of t 0, and the controllability Gramian matrix W 0 t is given by this expression. After substituting these values, phi values and b etc., we will get the value of the controllability Gramian matrix like this, and then the control is computed. Control for this particular system x 1 dot and x 2 dot is given by a into x 1 x 2 plus b into u, and if you have the any initial condition x naught and any final condition x 1, two vectors, then the control given by this expression will steer the system from the initial point to the final point. So, and we can observe that this given system is nothing but the harmonic oscillator given by this expression. The harmonic oscillator is so we have x 1 dot equal to minus, that is x 2, x 2 dot equal to minus x 1 plus u is the given equation in the example. So, this will imply that if you differentiate once again, we will get x 1 double dot equal to minus x 1 plus u. So, this is the familiar simple harmonic motion equation of simple harmonic, and with a external control u of t. So, this is the expression. Now, we can see that the control which we have seen in the equation 6, this expression is the best possible control in the sense that the integral from the time t0 to capital T of the norm square of this control is always less than or equal to any other control which steers the system from the initial condition to final condition. So, we can see that there are for a given initial condition and final condition, there may be infinitely many control. In fact, there are infinitely many controls for the steering of the system from the initial condition x 0 to final condition x 1. So, out of all these controls, so if let us say u of t is the control which we have obtained through equation 6, and u bar of t is another control which does the same thing, that is starting from x 0 to x 1, the solution of the system x of t. So, then we can show that this u of t given by the equation 6 is the best control and it satisfies this condition. So, in some sense in any control system, the energy of the control is very important. The minimization of the expenditure or the minimization of the energy is very important. So, in some sense we can say that this represent the energy of spent by the control, and it is the lowest one out of all possible controls which steers the system from x 0 to x 1. So, this can be proved by the following steps. Now, if you assume that there are two controls, so first control it takes the system phi of t 0 x 0 plus integral t 0 to t phi of t s b us ds. So, us is taking the system like this, and the other system is taking other control. So, here u is one control. So, the solution will be x of t, and u bar is other control. So, the expression will be different. So, that is y of t is the solution, different solution, but the final positions are the same for both of them. When we substitute t equal to capital T, x of t and y of t will be the same expression, okay, by the two different controls. So, that implies that when we substitute capital T in the place of small t in all the places and subtract this equation, we will get 0 equal to, these two expressions are the same, and so we will get T0 to capital T of phi of capital Ts b of us minus u cap s ds, because only difference is the u and u cap. So, we will get this expression. So, that is what is written in the slide here. So, we get 0 equal to integral T0 to T phi of this into whether it is u of s or u bar s minus us. Okay. So, this expression we obtained. Now, multiplying the equation by this expression, because if you recall the equation 6, the control specific control which we have. So, if you multiply both sides by this vector x naught minus phi t naught capital T into x1 w inverse transpose, if you multiply and see, compare it with the equation 6, we will get the u transpose s into this expression, because the portion x naught minus phi t naught t into x1 multiplied by w inverse, if you put it in front of this integral and combine it with phi t naught s into bs. So, that will give you u dashed, that is u transpose of s, and the remaining inside the integral is u cap minus u of s, and because it is 0 you can write it in any order. Now, we can get from this equation and from this fact, that is integral of u minus u bar transpose into u minus u bar. This is nothing but the norm of u minus u bar square. So, it is always positive. So, this integral is always positive value. So, 0 less than or equal to integral T0 to capital T of norm of u minus u cap square ds, this expression, and if you open the brackets and if you write like this, we will get norm of u cap square plus norm of u square minus 2 times u dashed into u cap. Now, from the equation 9 we can see that integral of u dashed into u, which is nothing but norm of u square, will be equal to integral u dashed into u cap, from if we take it to the other side. So, we substitute in the place of u dashed into u cap, integral of u dashed into u cap, we can substitute u dashed into u, which is nothing but norm of u square. So, minus 2 times norm of u square is obtained here, and already there is 1 plus norm of u square. So, it cancels, we get norm of u cap square minus norm of u square inside the integral, which is greater than or equal to 0. So, this automatically implies that this result, the result is this one. So, it shows that the control calculated by the equation 6, this is an optimal control, in the sense that the integral is the minimum out of all the controls which steers the system from x naught to x1. So, in the if the system is not controllable, is it possible to find a condition or find a control which can steer the system from wherever it can be controlled. So, if a system is not controllable, it does not mean that we cannot reach any position. In the state space, the system can reach certain points and it may not be able to reach certain other points. So, the collection of all the points where the system can reach as the end point, that may be a subspace of the state space. So, if x naught is the initial condition and x1 is a final condition, and if the system can reach that x1, is it possible to give an expression for the control, the optimal control as we have seen in the equation 6, is it possible to get a control in the non-controllable cases also. So, we have seen that the control u of s given by the equation 6 is optimal control in the sense given in the theorem that the integral of the norm of us square is minimized. So, now we will see that if the system is not controllable, that is if the controllability Gramian is singular, in that case is it possible to find a similar control as given in equation 6, so that it steers the system from initial x naught to the final condition x1. So, see, if a system is not controllable, it does not mean that from any initial condition we cannot reach any final condition. So, it only means that some final condition can be reached and some final condition cannot be reached. So, now we will see that for which initial and final condition one can find a control, so that the solution starts from x0 to x1. So, this particular theorem gives the result like this. Now, if you recall, the control given in the equation 6 is u of t equal to b transpose of t phi transpose of t0 to t w inverse multiplied by phi of t0 to t x1 minus x0. So, this control takes the system from x0 to x1 provided W inverse exists, but if W inverse does not exist, so here if you substitute, now if you substitute W inverse multiplied by this vector phi of this x1 minus x0 equal to gamma, then u of t is given by b transpose phi transpose into gamma. So, this is equation 6, but if W is singular, then the system is not controllable. In that case, what we can do is, instead of finding gamma in this way, it is not possible because W inverse does not exist. So, if W is singular, we consider the equation W into gamma equal to phi of t0 to t x1 minus x0. So, if the solution exists, if solution gamma exists for suitable right hand side, then we can find u of t can be obtained as b transpose t phi transpose T0 to T into gamma. So, in this case where the system is not controllable, then also we can find a control, but here the restriction is only for certain x naught and x 1 the solution may exist. So, we have this particular theorem. So, if the equation 10 W of T naught T into gamma equal to phi of T naught capital T x 1 minus x naught, if it has a solution gamma, then the control given by this expression B dashed into phi dashed into gamma, it transfers the system from the initial condition x naught to x 1. So, the proof is quite simple, that we write the solution expression, let x naught be the initial condition, we can write the solution as usual, and then in this solution if you substitute us as given in the previous equation, we will get x of t equal to the expression given here, replacing u of s by this one, and by making use of the equation 10 we will get x of capital T equal to the x 1, that is the final condition, by making use of the property of the state transition matrix. So, we have seen here the how to evaluate a control even in the case of a system which is not controllable. So, for suitable initial and final conditions. So, in the next lecture we will see the definition and some results about the observability of the time varying and time invariant linear systems. Thank you.